So we're going to have Ryan come up here and talk a bit about Project Tango, and we're going to have some show and tell on Project Tango. Thank you very much.
Before he starts, I would thank him for being such a great host and having Google.
Yeah, let's thank Brian for being such a great host. Actually, hold on. I got really busy and failed to reserve a room. And Art in the back, in the middle. Year and a half ago, former HBRC talk giver on his smart intelligent tripod using a Kinect, has arranged for us to have this room for the rest of the year. So thank you, Art. So tonight's talk has no slides, it's all demos.
Yay!
I just want to find the cable that I was using earlier. How many in the room have heard of Project Tango before? Oh, geez, okay. So no need to show the intro video. We will move right into the latest and greatest demos. For those of you who couldn't go to Google I/O, which is most people, I will show you all the demos that we gave there, including some new apps from some third-party partners. And I'm going to give you an overview of what Project Tango is and our latest device, this tablet. And then we will transition to specifically what Project Tango is good for robotics.
Don't knock that computer off.
It's a Chromebook. Not to say it's not a nice laptop, but in the demo they shoot them to show you that your data is in the cloud.
Well, then knock it off.
For those of you who have never seen or never been part of hardware development before, it's an excruciating process that is normally very hidden from public view. By the time you ever see a device demoed, they are typically what is called a PVT, a sort of a production validation test device. And if you look up on Wikipedia, you'll see EVT, PVT, DVT, and these terms. Never do you show EVTs or DVTs, which is a design validation test unit, in public. But we did, and we brought 30 of them to Google I/O. And we are a bit of a different project. Our intent is to open source our entire software stack, the schematics, the reference design, the firmware, and make it the most open sourced hackable phone or tablet ever. Having a hell of a time with these cables. All right. So now everyone can see the tablet screen. So I'm going to show you what is Project Tango. We have a unique device here, and I'm going to show you some of the sensors on the back. If we could get one of these to be the camera, that would be very helpful. Excellent. If you could zoom in on the tablet, right here in the middle is a wide-angle fisheye camera. It's behind this little black bar. I just flicked off the room, sorry. There's a wide-angle fisheye camera. So a mobile device has never had a 170-degree camera before. We're the first to do that. And we have a black and white global shutter sensor. So as I move around, if you see any blurring, that's really the screen refreshing, but there's no motion dragging. And if you take your cell phone that you have and you point it out the side of a car while you're moving and you take a picture, you know what happens is it looks all ripped and torn. And that's because the rows of a typical camera read off one at a time, from the top row down to the bottom. And during the time it takes to do that, even if it's only 13 milliseconds, your car moves. With this global shutter camera, all the pixels are exposed at the same time, and you don't get any motion blur. So that's never been in a mobile device before. We also have a infrared projector over here. So it's not on right now, but you can usually see a little bit of a red light when it is on. It's projecting an infrared pattern on the room at a 70-degree field of view angle that the camera on the other side here is seeing. And so we project on this side, we observe on this side from 10 centimeters away, and we triangulate the distance to objects in front of us. So it is essentially a tablet with an integrated depth camera. The camera that is sensing the infrared is RGB IR. Normally, a camera has a repeating pattern of pixels that's red, green, green, blue, red, green, green, blue, over and over and over. You get 2 greens because the silicon used is not very good at receiving green wavelengths, so they put 2 greens. We ditch one of the greens and we put an infrared pixel. So we're red, green, infrared, blue, red, green, infrared, blue. And so it's a color camera and a depth camera in one, which also has never been done before. So let me show you what we get out of that. So at the core of Project Tango is motion tracking. We do this by combining 2 different sensors. One is we have a 6-axis IMU. We have a 3-axis accelerometer and a 3-axis gyro. We also have the camera. We have the global shutter camera there. And you can see all these green dots is essentially using feature tracking to track interesting features in the room. You can wait a minute. Actually, this is a nice test. I'll hold still. Some of you wave around and you will find yourselves with red dots because you are outliers that do not agree with the world assumption of the device. So we've used these things together. If you look at the chart on the lower left of the screen, you're going to see the accelerometer and the gyro data. Those come in and they are time-stamped with an accuracy of 2 microseconds, alignment with the camera's exposure. So when we see one of these green dots on a particular feature in the scene, we know the relationship to the movement of the device within 2 microseconds. That hardware time alignment doesn't actually cost extra for manufacturers to do, but it's not something they do today. And so on Android, if you're running OpenCV or any other computer vision program, you're going to find plus or minus 400 milliseconds in your time alignment between your IMU and your camera. That does not make for good computer vision. So we're trying to make this a demonstration vehicle to show manufacturers that, look, you just run the clocks together. It's a little more complicated than that, but you don't need to add extra magical hardware to do time alignment. And then the last thing we do is we calibrate it. And most mobile devices today, this is the pass tail fest at the factory. Am I in portrait mode? Am I in landscape mode? Am I back in portrait? Pass. And that level of precision is also crap for doing visual slam and visual inertial odometry. So we actually put each device in a robot arm, and it spends about 10 minutes being moved around, taking pictures from all of the cameras in the back plus the depth sensor, and we calibrate the intrinsics of the individual sensors and the extrinsics between all those sensors so that we know how they are relative to each other. Of course, you can say, well, don't you have a CAD model? You know where the IMU is in relation to the camera, and so when the IMU and the camera move, you should estimate how they're related to each other. This is true, but when you manufacture a device and you make them very, very fast, the IMU and the cameras never land perfectly on the motherboard as expected. It's a little bit off, and so we calibrate for that. And that extra precision we find is important and valuable, and we're trying to demonstrate to manufacturers that it is something they should consider for all mobile devices. So I'm going to restart this app so that you can see a little bit more of the motion tracking. Okay, on the right hand of the screen, you have a top-down look of the location of this device, and that little cone is the view frustrum. You can essentially think of that as the camera's point of view. And if I move to the right, if I move to the left, it is tracking my motion. I can go in a big circle, and we can make circles with the device. And I'm limited by this cable, but I can go all around the room, I can go all around the building. There are no augmented reality markers or any special things needed for tracking this. Now, speaking of markers, we're going to do a test in a few months with some fiducials. And when I say we, Wayne has a thing for the robotics club to put fiducials on the ceiling and track those as robots move around. That is an excellent way to do things at low cost. The tracking that's happening on here is on an NVIDIA TK1 chip, which is the biggest, baddest Android mobile processor that exists right now. There are actually, I don't think, any devices on the market yet with this chip. They're coming out very soon. It is an incredible desktop class GPU in a mobile form factor. So you can't do this on a Raspberry Pi. Okay, so that's not an insult to the Raspberry Pi. That's just,
Well,
Yeah, it is.
yeah, it is. But
it
it is, but it's the truth.
we're going to sell this on our website for $1,024. So it's a different class from the Raspberry Pi. That's a developer price. The commercial devices made by LG next year will be much cheaper. Okay, so you saw motion tracking. There are three core techs that Project Tango has. The first was the motion tracking, and the second is this thing we call area learning. So this looks the same, but we should see off to the right 2 tracks. And what we're going to see is one track is the live visual odometry that is estimating where we're moving ever since the origin of when I started the app. The other one is recognizing places we've been before, and that's what's happening when the screen is freezing on the left. It's not necessarily the best user experience decision we ever made, but those little pink dots are basically features in the room that it's seeing again and again and again, and it's sort of recognizing that, hey, I've been here before. So the idea is that you could use this and map your house, and you would get an area recognition file of your house, and then your tablet, every time you pull it out, it will know exactly where it is. Of course, if you put the tablet on a robot, the robot knows exactly where it is. We think we can get down to about 5 centimeters of localization accuracy just using vision in a typical house, mall, or office environment. So that's 5 centimeter localization plus a pose of the device, so we know which angle and orientation the device is in.
How repeatable is it? You walk round back and forth enough and you end up back to the start point.
So using the area recognition works best if you do loop closure events. So ideally, I would make some counterclockwise and then some clockwise laps around this room over and over and over, and it would do a bundle adjustment on all of the observations of all of the features that it's seen from all of those poses, and come together with one estimated understanding of the area description for the room. And then when you restart the device, it just takes a few observations to sort of lock back in to any previous post. And in fact, that will be the challenge for game developers, is how do you make a video game where kids can take this, they get this fancy new tablet, they want to play a video game. How do you make it fun to do loop closure while you make that map? All right, the third piece of tech that we have is the depth sensor. And so this is showing you the Mantis Vision point cloud. So I'm kind of twisting the view frustum around as I'm moving the actual device around. You can see people a couple of rows back. We're basically targeting for 4 meters of distance, that's our goal. And we want to have less than 1% of distance noise over distance. So at 4 meters, we want to be less than 4 centimeters off in distance estimation. And we can return, we see the points count up here. If you look in the upper left, 6,000 points. If I look at a more flat surface, I'm going to get more like 12,000, 13,000 points. And we have an update coming that gives us 15 to 20,000 points per frame. So you can use this then to stitch together a map. So I'll
How's
show
that
you.
compared to a Kinect?
It is, the technology is similar in terms of its triangulation of infrared patterns. It's a completely different pattern than the Kinect use, as well as the Capri generation of prime sense depth sensor that we had in a phone. The Project Tango phone had the 2nd generation prime sense depth sensor in it, which was different from the Kinect. It never launched on any products, and then Apple bought them. So we may see that at some future point. That one shined points on the scene. and they would estimate the depth to all the points, and then it would guess and extrapolate in between all of the points. And so you would get a depth image back that was sort of VGA resolution, it would be called. However, most of the depth points were very much a guess and not very accurate. So this, we're giving you less points, but they're all individually accurate. But it is, you could think of it as a QQ VGA, a half VGA.
What would happen if you had two devices with the interference panels?
Possibly. So with a structured light projection, you have to be pretty close in your overlap. It is possible to have collisions. And so the stereo and assisted stereo solutions are probably better at avoiding collisions. Time of flight, probably somewhere in between. And we are open to all depth sensors. So this one has Mantis Vision. The phone had the PrimeSense tech. We also showed at Google I/O a time of flight camera from PMD Tech in one of our tablets. That instead of structured light is just a single camera. It's actually a completely different type of camera, and then a bunch of LEDs that are pulsing and strobing light over the room without a pattern. There's no specific pattern in its shining. Ideally, we hope that there's lots and lots of competition in mobile depth sensors, from stereo to structured light to time of flight and new types and beyond.
What's the frame rate of the depth sensing you're doing right there?
So we are running this at 5 to 6 frames per second. We'll probably settle on 6 for right now, so that you can run a game on top. So this GPU is amazing, but we want it to be amazing for games. And so the whole goal is to do all of that feature tracking you saw, the motion tracking, the sensor fusion, the 3D mapping, and the depth decoding using 10, maybe 15% of the TK1, so that you have most of it for your app. We could release future updates that maybe do 30 frames per second of the depth sensor if you didn't have a heavy gap app at the same time. All right, so let me show you what it looks like to make a map. This is early prototype code. This was done over the last few weeks from one of our interns. I was going to switch the camera so that both were basically showing the projection. But so actually, this was 2 or 3 interns that worked on this for about a month. It is not a production-ready API yet, but we can give you a preview of what it looks like to make a live 3D map from a mobile phone. And I'm moving somewhat cooperatively, but what I'm not having to do is pay attention to the geometry overlapping between frames. A lot of the different SLAM techniques that you'll see out there require you take the geometry from one frame and you align it with the geometry from the next frame and you build up your map that way. But because we're using the Project Tango's motion tracking, I'm really not paying attention to where I'm walking, and that was interesting. We have a feature that would remove moving objects. I guess that is not on right now. That's interesting. So making a map, and what I'm going to do is zoom out so you can see a little bit more of the room that I'm mapping. Oops, there we go. So I'll just finish over here going to this corner. Or not. So I'm going to pause the map, and what I'm doing right now is I'm not adding to the map, but I'm just walking around in my map. So imagine that I had scanned this whole room and spent more time doing it, and then maybe we did a little post-processing cleanup, and now this is a virtual game. And now I can run around, and I could maybe bounce balls around, or have virtual characters that are running around on the floor, and we could be interacting with them. They could be running under chairs and under podiums. So you now have on your phone, you have SLAM, 3D mapping, and VR. So there's the room. And if I hit save, it may end up crashing, but it saves out a PLY file. So anyone familiar with 3D file formats, you know you can use a PLY. Now, I'm going to show you a little bit of the precision of the motion tracking. I'm going to come forward here. I'm going to zoom in. And for those of you who like maybe artistic things, so you could imagine doing some, not surprised, virtual painting, let me show you. So I'm going to attempt to write my name in the sky just using the camera and motion tracking. There we go. There's 3D cursive Ryan. All right, so that's the tech. We're going to get to robots in a second, but let me show you a little bit of what some people are doing app-wise. These apps are not robot-specific, but at least you can think of new ways maybe this tech would get used. So the first one, this was done by Unreal Engine, and so when we say that there's a beefy GPU in here, the Unreal Engine running on a mobile device is very new. And this is a very heavy graphics demo. What we did was we basically hooked in the motion tracking of Project Tango into the virtual camera, and I can now walk around in this scene. And you may have seen a lot of things where you can pan and tilt. Pan and tilt on mobile devices today using the gyro is fine. There's lots of things for that. There's a game rotation vector in Android you can tap into, but you're going to drift eventually if you're not using the camera. And one thing you can never do is translate. But with this, we can go translate, and we can walk up to things, we can walk away from them, and we can walk all around the scene. Now, if you're a game developer, or if you're a movie director, and you want to capture a virtual camera path, you know that that is often very difficult to do in your virtual editor. You're trying to make a natural human cameraman-looking motion in a virtual environment. That's very difficult. So what I'm going to show you is that I can play out a little scene here. I'm going to hit record, and I'm going to say, oh no, there's aliens coming in the roof. Let me run over here, and okay, now we're going to go over here, and we're going to look out over the balcony, and then we're going to look back at the roof. I can hit stop, and I can just set the device down and hit play, and it's going to play back my motion. So you essentially have a very precise 6 degree of freedom motion capture system built into your tablet.
Which Google Office was that?
That's the executive bathroom. That's what that was a model of. All right, so if you had that motion and you saw the 3D mapping of the room. Now, give a little faith to what might happen as that mapping improves. The resolution will improve, the color quality improve, the post-processing will improve. Imagine you can map your house and you get it to look like this. Now you can walk around your house, or you can send a file of your house to someone else to walk around your house, such as your prospective buyer, a client, a home remodeler, you name it. And if you're anything like me and my wife, she has ideas, I have ideas. It usually requires a lot of sweat to move the furniture around 27 times until we agree. This makes it much easier. I can just tap this chair, and I can just move it, and what we can do is we can say, okay, you think that's a great spot for the chair, let's go pretend to sit there, and can we have a nice view out the balcony? Can we see down the hallway? Okay, we can agree that's a good spot. Whereas if I move this couch like this, we could maybe agree that that's a bad idea before we even try it. And so what Project Tango gives you is a sense of scale. You get this full motion in the world as you move around. So you gotta have a little bit of fun. And zombies are all the rage, right? In movies and TVs, everybody likes zombies. Well, in this game, we're going to kill them. This is from Limbic Labs. They had one of the most popular iOS and then Android games on the market called Zombie Gunship. And you're basically in, you can sort of see a picture of it, you can't see it on the projection. You're in an AC-130 gunship. The gunship is flying around. You get to man the gun, and you get to shoot the zombies. But you can't control the plane. So they made Zombie Gunship reality. We don't have any audio. I get to imagine being in a drone. I can go anywhere I want in this scene. Got the Statue of Liberty over here that I'm supposed to be protecting. And I'm just going to start blasting some zombies. And because we have scale, we can get down low. There's some zombies eating a human. This is an infrared camera, so the zombies are black, they have no heat, and the humans are white. But we can get down under treetops, because we're in a drone, and we can shoot the zombies from wherever we want. So imagine if one day you were to open a game like this, and it were to ask you to have a quick look around your living room, and then instead of this sort of canned island scene here with Statue of Liberty, it was a dynamic scene that was adapted to your actual house. So I have 25 seconds left. I only have 38 kills. That's actually pretty terrible. All right. So I have one more thing to show you that's quite experimental, but I'm going to look for a volunteer. Excellent. Thank you. If you could stand right here. Art, can we get the camera on her? Just on her.
No pressure. No pressure.
There's this company called Dive, which I'm just showing the logo here. They make a little snap-in thing for your cell phone. You can snap your cell phone in, and they have these cool little things where you can tilt around and you can see these little virtual experiences. Someone took a Project Tango phone and shoved it in one, and we were blown away. So then we asked them, can you make a 7-inch version? So this is their 4th iteration of an HMD for a 7-inch Android tablet. The first and second versions were 3D printed. The third version was on a very high-end SLS printer, and these were actually CNC'd at a factory down in China, and then sent here and had the final assembly done. I am going to put this on your head. So bear with me.
Take off my glasses?
Sure. Don't tell everyone your name, where you're from.
Hi, I'm Shiloh. I'm from Sunnyvale.
Thank you, Shiloh. There you go. Just in here. And you can hold these forward and back until they're in focus. Usually fairly close to your eye is where the focal point is. But since you wear glasses, you may need to make different adjustments. So what she is seeing is, she has 2 lenses, and she's seeing basically both of those scenes of 360 world, hopefully aligning fairly reasonably, and a shark swimming in 3D in front of her. We are now going to venture onwards. Are you ready, Shiloh?
I think so.
Okay. All right, hold still. Loading. There we go. Now what she's seeing is all of you flooded. Go ahead and duck down. So it looks as though the room has been flooded. We have a whale, we have various fish that are floating around. And so actually, Shiloh, you can get up and walk, and I'll just make sure you don't hit anything. But you should be able to see through the camera. And now she's above the water, but go ahead and duck your head down again. There you go. Every time you go down, there's some bubbles. And so you essentially have untethered virtual reality, or mixed mode reality, because she is seeing through the camera and the virtual world together at the same time. So I'm going to do one more. Is that okay, Charlotte? Okay, one more. Let's give Shiloh a hand for being a big sport. So clearly we need a better user interface than popping this thing in and out every time you want to switch an app. We'll get there. Okay, now I'm going to ask you to take one step forward, one step to your left, or actually, I'm sorry, rotate to your left. There you go. And one step to your right.
Right over the
Perfect.
trapdoor.
Okay, here we go. And we'll hold still. Oh, it's drifting. Oh, there it goes. Okay. You can go walk. You're good. So for some reason, it does seem to be drifting a bit more than we would like. But she should be able to walk around and experience things. This is not mixed reality. She can't see through the camera, so she could run into things. So the mapping that we showed you earlier is obviously key for experiences like this to really pay off. And the ability to walk around a room, make a 3D model, have it transformed into some virtual land, some jungle or some cliff, and then walk around and experience some place that you've never been before, but it matches the geometry around you, is going to be brand new. If you lean over, Shiloh, you should fall. If you lean over too far.
I don't want to do that.
Okay. Yeah, if you walk out on that plank, which is kind of hard to do, I've actually worn this and put on headphones so I don't hear the ambient sounds around me, and it is hard to convince yourself to jump off the ledge just by taking one step forward. I've actually found myself sort of tapping to make sure there is real floor there. Cool. Well, thank you, Shiloh. Let's give her a hand. Okay, now on to the robots. So has everyone seen our most recent robot video?
Yes.
No, okay.
Yeah.
So I will show that while Ted and you guys get ready to show off the actual live integration. So don't plug in yet. Journey video. Cool. Oh, it's extending my screen. Thank you. Not what I wanted. Cool. Okay. Audio. All right, we'll just give this a go. Art, back there, do you know how to get audio?
No, sorry, I'm not sure what's going on.
Hold the mic to the speaker.
Yeah.
Hold the plug.
Yeah, it's actually not playing any sound locally either. I can't fix that.
Like the headphones.
There's no headphone plugged in either.
Research labs and industrial partners to bid.
Man! What are you doing, Art?
Buttons!
Okay. We're gonna try something else.
Industrial partners to build upon.
Oh, oh.
Point the camera at the left.
Yeah, there you go. Nope. Oh, it's still seeking. Give me a second.
You just have to skip
There we
this.
go.
Yeah,
It's
it's working.
You know,
We're missing the channel.
And audio.
no.
Uh,
Undo the
Okay.
Just undo the audio.
All right, Art, we're gonna do camera on
Build upon
screen.
the last decade of research.
Zoom in. Enhance. I take everyone to see that skit. Enhance. Worst YouTube demo ever.
You can actually see us immersed in that environment.
My name is John Ely. I am a technical program lead. Decade of research in computer vision and robotics, concentrating that technology into a very unique mobile device.
When you're outdoors, you can use your cell phone and you can use GPS and find where you are and where you want to go. When you enter, the moment that you enter a building, GPS is not available anymore. So we need to create other ways for being able to find where we are.
Project Tango is producing a solution to the visual navigation problem for how devices can stay localized in 3D space.
I did the research initially that developed the 3D vision algorithms that the rovers use to drive safely on Mars, and I worked on that as a grad student in the 80s, and then I came to JPL, and then it turned out that Tango is similar in that you've got this device in your hand, you need to know where it is. One of the best ways to do that is to use the camera in the device to track features in the room.
The problems we encounter in that research are the same problems we're struggling with now in our autonomous driving project and in the Project Tango, which is how to re-recognize places that you've been before, even though the environment has changed.
We have runs throughout the DC area where Project Tango is recording all of the visual and also inertial odometry information from the vehicle, and then we use that to experiment on localization algorithms.
So our team at ETH is working on search and rescue using small UAVs.
When first responders arrive at the scene, they often want to get a map of the environment because buildings are destroyed and previous maps are not valid anymore.
So my team is contributing a number of different algorithms to Project Tango. In particular, we're looking at making it possible for Tango devices to also work outdoors in terms of capturing depth information.
So one big goal we have at ETH Zurich is building a map of the city and the lake area. I'm very enthusiastic about bicycling, so the natural thing to me was to mount the helmet with the phone and to just go through Zurich.
We actually feed that into our maps, build these big maps together that all the robots can use.
Once navigation and perception is solved for a single robot, you can combine it for aerial vehicles and ground vehicles and all co-localize in a common map.
And so it's a very exciting thing to try to be part of because you'll be able to have a very large impact for computer vision and robotics and 3D modeling.
We were working very closely with Johnny Lee. I was fascinated by the way he brought in all specialists from robotics, like navigation and perception and calibration. He got the experts from all fields and brought them together to build one device.
we've been able to work in collaboration with universities and other industrial research labs to push the limits of physics and push the limits of our human knowledge to achieve much more than we could alone. And I want to work with the developers who are excited about doing more than the touchscreen app and help us explore this journey. And as we evolve the hardware, we are excited to see what the developers will produce.
We launched that video just before Google I/O to make sure everyone knew this is not just a Google effort. There's lots of really great research labs contributing, and not just the students who are there now contributing, but as you saw, like Larry Matthews and Sturgios, when they were students, they were breaking ground on some of this tech that we all use today for robotics, for SLAM and computer vision. And the decades of work that went into it and used to require a desktop computer now can be done on a mobile device. But without those decades of work, we would be nowhere. So we made that to thank them. So now we're going to show what Ologic's been up to with doing some live integration of Project Tango data and motion tracking and sensors with Ross.
Okay, so I'm Ted Larson. I'm a member of the club. And like Ryan, I have a big interest in robots too. And we've been working, I run a company called Ologic. It was founded by me and another guy that we met in the club like 10 years ago, Bob Allen. He never comes to meetings anymore because he moved out of the area. But
came to Robo Jam.
He did come to the Robo Jam.
Yeah.
I saw that. Got to hang out with him, have some lunch. Anyway, so we have been working on integrating, oh look, here you go. You got it on the screen. We've been working on integrating Project Tango with anything robotic oriented that we can come up with. One of the items that we've been fooling around with was, Tango's cool and it can do some amazing mapping and visual odometry, but what if you could take that and just bring all that data into ROS and then bring that to bear on a robot immediately so you could use it. Step one was we needed a ROS node that ran on the phone that could publish the data that Tango was generating, and then we could visualize it. Oh, weird. He's still working on trying to get the resolution right so that it
can show the entire screen.
Yeah, so we can show the entire screen. So what we did was a couple of things. We had a couple of interns this summer, Rohan being one of them, and we put them to use working on some Tango-oriented items. And one of the items that we were working on was what kinds of interesting things that could we do if we visualized the visual odometry with it. And we're going to see if we can, we may end up having to do the same trick we just did for the video. Oh wait, is that it? At the whole screen? Excellent. Okay, so he's trying to get RViz up and going here so that we can run the application. So let's see, I'll talk about some other things that we've done with this while he's finishing and making it work. We had another intern this summer, a 17-year-old who is Tony Pratt-Canis's prodigy that he's been mentoring. And we gave her a Tango phone and said, look, let's have you build some interesting 3D maps and document the process really, really well so that other people can not only make maps but quickly build quick Unity frameworks so that you can walk around inside the map that you've made or drive a robot around or roll a ball around inside of the 3D map that you've made. And admittedly, she's an extremely bright 17-year-old, but she was able to, within a very short period of time, pull the 3D data from the phone and then integrate that with Unity and make a Unity app that she could walk around in or push a ball around in. And it wasn't tremendously difficult. So at least for her it wasn't. Now maybe other people it might be.
She's a saint, because our SDKs were not good at the time she started that.
No. And she's documented it all, by the way. It's out on the web, and there's some YouTube videos. And then what Rohan here has been working on with another guy, Ologic, Brandon, who I guess is not here tonight, but he was going to come, is this, which is, this is taking the visual inertial odometry and visualizing it in RViz. So you can see he's holding the phone here, and there's a virtual 3D phone that's kind of floating in space, and it is tracking where he is. So why don't you go ahead and go for a walk, and we're going to see as he walks around here, it's going to track his motion in 3D space as he moves. So he'll go to the back of the room and then come around. And as he does more and more laps here, it'll actually do loop closure, and it'll actually line up really well. He's going to go all the way out of the frame. Okay. But anyway, as he comes around the room here, he should eventually, as he arrives back over here, end up roughly where he started. And that was a pretty long walk. So if you think about drift and odometry and IMUs and things like that, this is incredibly difficult to do. And like, we've built robots here in the club where we've tried to do, just basic wheel odometry to drive around on the ground and just try to keep track of where we were as we moved and be able to arrive at the same point in space where we left from after going for a little drive or a walk or whatever. And I've never been able to do it as well as this does.
Okay. Yeah.
And now it's drifting.
Yeah.
Most of the time that doesn't happen. But to be able to actually have this accurately work is pretty interesting. So now that we have the ROS pieces, we also have the ability to, the second demo he's going to show is visualizing the depth data, again, in RViz. So publishing the depth data out of the phone and then being able to bring it into ROS and then do something useful with it. So with these things combined, we could very easily build a robot that you walk around a path and then you put the phone on the robot and say, go follow the path that I just walked, and it could do it. And when it has the depth camera going simultaneously, which in this case he's visualizing the crowd in 3D here, so you can see all the people out there. There's a bit of a lag because we're running it over a really slow Wi-Fi. But as you could conceivably have these two pieces running together on the phone and then running a robot that not only can follow the path that you followed, but it won't run into anything. And new obstacles could be presented in front of the way, and it would be smart enough to go around them or avoid them or whatever. And so here's the interesting thing. This indoor localization problem is just going to be solved in a mobile device. Admittedly, we spend a lot of time with robots that that do run ROS, where you can take a laser rangefinder or a Kinect and try to make a map of the room using G mapping, which we all know in ROS. Those that use ROS, G mapping is awful. It doesn't work very well. It produces these funky maps that you have to spend a lot of time cleaning up by hand in order to make them better. We spent some time with the Ubiquity Robot project, a lot of people in the club are doing that, making maps of the Hacker Dojo with a laser rangefinder. It took a really long time to get a really good map by the time we actually were done. Whereas one of these devices, you could just go for a quick walk and boom, you have a map, and you wouldn't have to spend weeks and weeks trying to figure it out. So this kind of stuff that they're working on has the potential to leapfrog a lot of the things that we've already been doing, but really augment items that are going on already. It replaces certain key pieces of ROS, but then there are other pieces you'll still need. So the idea that we can integrate it all together and have one big happy mashup soup of all kinds of tasty bits and bytes seems pretty exciting. So anyway, we're going to continue playing with this and developing more things that will integrate ROS with this. This whole project, Google's graciously said, go ahead, share it with the world, open source it. So all of the code that runs all this is open sourced, and it's on the internet. It's on GitHub. And if you go do a search for like ROS and Tango, it shows up. And our GitHub repo is standing, our GitHub repo moderator is standing right here. So if you decide to merge or branch or whatever, if you fool around with the code, you'll probably get an email from him this summer.
Cool. Well, thank you guys.
Yeah. Oh yeah.
I know we want to get out of here early, but maybe we could take a few questions. To share, I always hate when there's a demo and some of you in the audience may be like, oh, I want to play with that, but you don't have this device. We can't make these anymore. It has a prime sense depth sensor owned by Apple, and there's other legacy components in there that just don't exist anymore in the world. But the new tablet will go on sale later this year, not far from now, to developers. So at $1,024, this is probably not the thing you want to get for your personal tablet, although it is the highest end Android device that exists. It has 4 gigs of RAM, 128 gigs of storage, an LTE modem. It's the highest clock TK1 possible. It's a beast, but maybe you can get your company to pay for one. LG has announced that they will ship a commercial device next year. So for the next 12 months, this stuff will be limited. There's very few people who will have it. Hopefully some of you get to have a tablet. And then at some point next year, let's say maybe third quarter or fourth quarter of next year, that at a normal commercial price point, you'll be able to walk into a store, a Best Buy or a Carrier, and just get a device that has this built in. Go ahead.
What are the features that the developer modeler is going to have versus the commercial one? I mean, usually the commercial ones are locked down or restricted, or there's extra features, there's crapware.
Well, the nice thing is this is our tech, and we're going to ship pure vanilla Android and no bloatware, and we want to keep it that way. The goal is to be open and hackable. I don't know for sure whether LG would keep it in unlocked mode, but we do want to support the Android OEM unlock, and we do want to not fill it up with bloatware. But that will be LG's product. This one for sure is hackable from the get-go and comes with no additional apps. We're also going to send one of these to iFixit. We sent the phone to iFixit, and they did an awesome teardown of the phone. So they'll do a teardown of this so you can see all the details and all the components. One more set of people to thank, if I may, real quick before the next question. Ted and Rohan have been awesome at Ologic. They're hosting a GitHub repo for raw stuff. OSRF, if we have any open source robotics foundations, there's Kelly in the back, has also been phenomenal. They posted a blog post about what Ologic did, and they've contributed a lot here. Bosch is now contributing to ROS plus Project Tango, and University of Massachusetts Lowell has a big robot lab, and they are going to be hosting the website that will be sort of the official website of all things ROS and Project Tango together. They've kindly offered to do that, to collect all of them together at a university, so there's no commercial interest there. So I just wanted to thank all of them. Other questions?
You said it's open source, hackable to the hardware level as well. Are the components just off-the-shelf components? Can somebody buy the bill of materials and put one together themselves, or do some variation on it themselves? Or?
If you don't want a tablet, can you just, if you want to take like a robot?
Sensors and that sort of stuff?
So the question is about availability of the sensors for something other than a tablet. I have not made this type of hardware before, but for not too much money, you can get not an individual, but for a company, it's not too much money to get a Taiwanese ODM to make you a device with whatever parts in it you want. But for those of us who want to hack at home, unfortunately, I don't think any of these components would be available. There's just no supply chain for them. The price is reasonable. I mean, most people may not realize, but the front camera in your cell phone probably costs 80 cents to $2, and the rear camera The high-end, really nice ones are probably like $20. They're not outrageously priced, but that's when you buy them like 100,000 unit volumes and so forth. So you can't pick this stuff up in a drawer in Radio Shack. We do realize there's a desire for these sensors and actually the whole stack to perhaps exist as a module. We don't know when the right time to pursue that would be, but as this tech matures and the parts shrink, we do want to see this in phones, wearables, and other things. And as we approach the ability to put this in a wearable, you also then have the ability to make it a little dongle and you can stick it on a robot as well, but not immediately.
Right, so I guess that's a similar question. If I had equivalent sensors, maybe not exactly the same as a software module enough that I could integrate it.
Yeah, so for equivalent sensors, I think, so there's a thing called a Jetson board from NVIDIA that has the TK1 chip in it. It's very low price development board. Lots of I/O pins and camera module adapters. You could hook up a camera of your choosing, so long as you could get the drivers to work or whatnot. I think it may come with one camera, I'm not entirely sure. You could run this software stack on the Jetson board, and you could make that the main board for a robot or machine or device. It doesn't have to be our cameras, but you would have to do that work of getting the drivers to work, adapting and tuning and so forth. It's not yet plug and play. Go ahead.
The outdoors question. You knew it was coming.
I don't know where I put my device. It works fine outdoors or indoors. I presume you're talking about the depth sensor.
Direct sunlight.
Yeah, so I'll just start with the motion tracking camera. Its requirement is light. So in a completely dark room, the motion tracking camera doesn't work and it will drift off on you. I've gotten the tracking to work fairly well in my bedroom with just the television on. When the exposure's tuned just right, that's about enough light for the motion tracking to work. And then of course out in the sun, it works great. The depth sensor is infrared, and so it has to fight ambient light. Most depth sensors, I should say the Connect generation, were continuously on. And so for 1,000 milliseconds a second, they were constantly spreading light out over the scene. And they're limited by eye safety, by how much light you can shine. We instead, if you remember the question earlier, we run at 5 frames per second on the depth. That's because we do a very, very short, very, very bright pulse that overcomes a lot of the ambient IR. And in the shade, it works fairly well. In direct sunlight, in the middle of the day, sun hitting the ground, you're not going to get depth back. But when you're in the shade or in the evening, it works fine. I've mapped my house several times at 2 p.m. and gotten portions of my backyard missing, and then sort of 7 p.m. when the sun's going down, I was able to map my whole backyard. More questions? Anything for the Ross experts? Tully.
Comment on the jetpack. I believe Austin has one and is playing with it, and there was NVIDIA's just talking about coming to RossCon to show off Ross on it.
That's awesome. So it's not a question, just a statement of NVIDIA standing behind Ross on the Jetson board. That's fantastic.
And we have a Jetson board at Ologic, and Andrew, who's missing, but he's our other 12-year-old intern this summer.
Do you hire adults?
No. I only get the kids. Because
The question is, are there any adults there?
There's adult supervision, but the kids don't know. The kids don't know what's impossible, so they just push ahead and do it anyway. So he's actually been trying to reproduce Austin's work on Ross on the Jetson. So hopefully by the end of the summer we'll be able to get him to bring it in and show it off. So
I do recommend. I recommend we wrap up with traffic.
We're playing with.
Playing with fire.
We're playing with fire. I don't know why this is.
And the band is Arcade Fire.
It's Arcade Fire. So it's I have a request. Please dump your badges in the box as you go. They actually cost money.
So thank you all for coming,
Thank you.
and thank you for all the presenters today.